Hello, welcome to Electronics Education. This is Vincent Chang. In the previous lecture, we analyzed the ideal series shunt feedback. So in this lecture, we are going to talk about an opposite topology, which is the shunt series feedback. Shunt series feedback. So feedback part 4, shunt series feedback. So let's quickly review the 4 topology. The first one, voltage amplifier. So what type of feedback topology associated with tied with the voltage amplifier? Series mixing and shunt sampling. What about current amplifier? It's the opposite. So it's the current mixing and then current sampling. So shunt mixing and series sampling. Shunt series feedback. What about the third one? Transconductance amplifier. So voltage input and current output. So voltage in should be series mixing and current output should be series sampling. So series feedback. The last one, transresistance amplifier. So it's the current mixing, shunt mixing, and shunt sampling. So shunt feedback. All right. So when I go through this, so maybe your focus is on the top of the slide. So also you have to pay attention to the bottom of the slide. All right. All right. So the signal is always changing. For example, in this case, it's the IS minus IF equals II. Look at the circuit diagram. And then the circuit diagram on the right, what's the signal of the amplifier's output? It's the voltage output VO. So let's focus on the shunt series feedback. Current amplifier, shunt mixing, series sampling. So let me tell you this. I position my responsibility. It's not, of course, all the result has to be supported by math. But I don't want to spend much time on the mathematical derivation, okay? This is not what you need me the most, okay? So I want to spend more time on the concept, on the key concept, and also the skill to analyze the circuit. Shunt series feedback, current mixing, and then current sampling. So current mixing, IS minus IF, let's focus on the equation. IS minus IF equals II. So in the series shunt feedback, we talk about KVL. So now it becomes what? Becomes the KCL. All right, so check the node, the input node. The current flowing in is the what? Is the IS. So equals what? Equals II plus the IF. Therefore, the II, the input current, should be IS minus IF equals II. IS minus IF equals II. And so II becomes the amplifier, the input current of the amplifier, and then current control, current source, Norton equivalent. The current control, current source, the II. In parallel with the output resistance, Norton equivalent of the current amplifier, and then the current going to the output. But in the ideal case, there's no external load, no resistance, zero load resistance. Therefore, there's no current flowing through the RO. So IO equals AII. II, so I want you to pay attention to the circuit, all right? So there's no resistance between G and H. There's also no resistance between E and F. Therefore, there's no voltage drop across RO. So no current going through RO. Therefore, the IO equals what? Equals AI times II. Why this is important? Because this is important. Why? Because this is the ideal case. This is ideal case. If you put a load resistance on the left, let's say if you add a load resistance between G and H, then ideal equation will be broken. Okay, this is going to be the practical case. We're going to deal with this in the future. But in the ideal, pay attention to the ideal shunt series feedback. I on the left, II times AI equals IO. On the right, the ideal structure tells us the II times A equals IO. Equivalent. They are equivalent. And the last one, current control, current source. IO times beta equals IF. Current control, current source. So again, three components. RF, closed loop current gain, and then closed loop output resistance. Norton equivalent. Norton equivalent. In the ideal case, there is no resistance between G and the H. The first one, because it's the ideal case. It's the equivalent to the ideal structure. So there's no surprise. There will be no surprise. This relationship still true. This relation, the relationship between open loop gain and the closed loop gain remain the same. Remain the same. The only difference from the past, from the previous in the series shunt, is that we put the meaning for the amplifier. So now the nature of the amplifier becomes the current amplifier. So A is now defined by the current gain. Also, the AF is defined by the closed loop current gain. It's now AIF. What about the closed loop input resistance? Maybe you can forecast. You can just maybe, let me ask you this. When you have the feedback, the shunt mixing, the input resistance is going to change, right? Compared with what? Compared without feedback, the RI. So when you add feedback, the input resistance is going to change. But because of the shunt, so then in the series, it's got increased. But what about the shunt mixing? So you think the IF is going to go up or go down? Let's see. According to the definition, the voltage input, the voltage is the VI. And now the current in is the IS. Then you can prove. The relationship between RI and the RF is this. This derivation is very, very clear. So if you are interested in the math, you can just stop. Because I said, I don't want to spend time on the math. I think it's your job if you are interested. But if you are not, just focus on the conclusion. All right? So conclusion is this. Through shunt mixing, the closed loop input resistance is going to be reduced. By what? By the same amount of feedback, the same factor. The amount of feedback, 1 plus A beta. But the A is the current gain. Also, the beta is also current divided by current. The feedback current divided by the output current. The final one, the closed loop output resistance, the ROF. The resistance looking backward, the circuit, the ROF. So again, what's the first step? When you deal with the output resistance, remove the signal source. Let IS equals 0. And then what? Then you put on a testing current. You put on the testing current and try to measure the voltage across the output terminal between G and H. The ratio between V and IT will give you the answer. All right? So again, just try to find out the relationship between those variables. In this case, the IT equals what? These two current. The first one, V divided by RO, Ohm's law, and then AII. Because your goal is to find out the V divided by IT. So you have to replace the II. You have to replace the II. So how to replace the II? II, look at the left-hand side. II equals what? Equals negative beta I times IT. And try to replace IT with what? You don't have to replace, just go to the left-hand side. And then here's the answer. Here's the answer. Very easy. The conclusion. If you do the series sampling, the output resistance is gonna go up. It's gonna increase by the amount of feedback by the same factor, 1 plus A beta. So here's the takeaway. Current amplifier. We can consolidate the feedback structure into a more simple one. So current input, IS, the current output, IO, Norton equivalent. Is the Norton equivalent. For shunt mixing, shunt series feedback, so shunt mixing, the input resistance is going to go down. It's going to be decreased. It's going to be decreased by, divided by 1 plus A beta. For the closed loop gain, the unchanged. But for the output resistance, because it's the series sampling, it's going to go up. It's going to increase by times 1 plus A beta. I think this is very, very, we kind of try to warm up and going through all the topologies. Because it's the ideal structure. Ideal series, shunt feedback. In the previous lecture, this lecture is the opposite of the series shunt, ideal shunt series. So I think those two type of different opposite topologies sort of they give you the answer or instinct for the last two topology, which is the series feedback and the shunt feedback. So I look forward to seeing you in the next lecture video. Thanks for watching.